Imagine an aircraft with skis as long as a school bus and powerful rocket boosters, each capable of generating up to 1,000 pounds of thrust. That's the LC-130, an engineering marvel with a unique jet-assisted takeoff system, with main skis measuring 28 feet long and 4 feet wide. The LC-130 is capable of landing and taking off on harsh ice and snow surfaces that conventional aircraft cannot access. But what makes this aircraft so special? How does it cope with the extreme conditions of the Arctic? Discover the secrets behind the LC-130's extraordinary capabilities, an indispensable aircraft for missions in the coldest places on the planet. Evolution of the LC-130 platform. The development of the LC-130 began with a groundbreaking prototype in 1956, when engineers modified a standard C-130A with ski equipment. Initially, this experimental conversion proved successful, leading to the modification of 12 additional C-130A models with skis and specialized hydraulics under the designation C-130D. The transformation from a conventional LC-130 to an LC-130 involved substantial modifications. In 1959, the first for factory-equipped ski-based Hercules were produced under the Navy designation UV-1L, based on USAF C-130BS models. Subsequently, the designation changed to C-130BL and later to LC-130F in 1962, when aircraft nomenclature was standardized across all services. The LC-130's evolution introduced significant technical advancements. The integration of advanced T56-815A3, 5 engines and NP2008-bladed propellers brought substantial improvements in performance. These upgrades provided a 20% increase in fuel efficiency compared to the previous 3. Zero-engine enhanced the aircraft's cargo capacity for operations in remote polar regions, and reduced maintenance demands as well as inspection times. The LC-130's development history reflects a legacy of continuous innovation and adaptation to meet the challenges of polar operations. The journey began in 1956 with the creation of the first prototype, which was developed by modifying the C-130A to include skis for snow and ice landings. By 1957, the aircraft entered its initial testing phase, successfully demonstrating its capability in extreme environments. In 1959, the first for factory-equipped ski-based Hercules aircraft were produced, marking a significant step forward in operational readiness. This milestone was followed in 1962 by the standardization of the designation to LC-130F, solidifying its identity as a specialized polar aircraft. The development continued with the introduction of the LC-130R model in 1968, which brought further enhancements to meet evolving operational requirements. In 1974, the National Science Foundation received the first of 3 replacement aircraft, ensuring the continuation of its polar research missions. The delivery of the final 2 replacement aircraft was completed in 1976, marking the culmination of this phase in the LC-130's storied history. Furthermore, recent upgrades have enhanced the aircraft's capabilities. The new engine configurations allow the LC-130 to create equivalent thrust as JATO bottles while operating at lower temperatures, consequently making them more environmentally friendly. During the transition from 4 to 8-bladed propellers in 2018, maintenance efficiency improved dramatically, reducing engine downtime from 36 hours to approximately 2 hours. The continuous evolution of the LC-130 platform demonstrates the ongoing commitment to improving polar aviation capabilities. The aircraft's modifications have consistently focused on enhancing performance, reliability, and operational efficiency in extreme environments. Ski system engineering. The engineering marvel of the LC-130's ski system represents a sophisticated blend of mechanical innovation and cold weather adaptation. The aircraft's unique capability to operate on both snow and conventional runways stems from its advanced retractable ski system. The ski system's engineering, specifically, addresses the challenges of polar operations. Indeed, the retractable skis enable the aircraft to land on snow and ice, while maintaining the flexibility to operate from standard runways. This dual-mode capability particularly stands out in missions supporting scientific research stations, where the aircraft must transition between conventional airports and remote polar locations. The materials used in the LC-130 are designed to meet rigorous specifications, ensuring reliable performance in extreme temperature environments. These components are engineered to withstand sudden temperature variations that can cause thermal shock, as well as the adverse effects of extreme cold on lubricating systems. The aircraft is built to handle the challenges posed by variable snow and ice surface conditions, with particular attention given to preserving material integrity in frigid climates. Furthermore, its design includes specialized hydraulic systems capable of maintaining full functionality in sub-zero temperatures, ensuring operational efficiency in the harshest conditions. The maintenance of the LC-130's ski system requires a highly detailed and precise approach to ensure operational safety. Key protocols include regularly inspecting fuel vents to prevent the accumulation of ice and snow, thoroughly checking drain holes in the control surfaces to avoid blockages, and systematically examining the ski attachment points for any signs of wear or damage. Additionally, the hydraulic system's performance must be carefully monitored to ensure it remains fully functional under demanding conditions. For optimal performance in polar conditions, maintenance crews must ensure that all drain holes remain clear of debris and ice, as trapped materials could lead to control surface imbalance. The aircraft requires specialized care once it becomes cold-soaked, necessitating specific procedures for basic operations. Surface evaluation presents a significant challenge, specifically regarding changes in surface definition based on weather conditions. Maintenance teams must be particularly vigilant about potential deep cracks or fractures on ice sheets and glaciers. The comprehensive maintenance approach ensures the ski system's reliability in environments where equipment failure could have severe consequences. JATO system integration. The JATO system represents an essential engineering advancement in LC-130 operations, enabling crucial takeoffs from challenging snow and ice surfaces. The system utilizes 8 solid fuel rocket bottles, with 4 mounted on each side of the aircraft. The JATO configuration delivers impressive power through its strategic placement. Each rocket bottle generates approximately 1,000 pounds of thrust, creating a combined additional thrust of 8,000 pounds, primarily designed for snow and ice operations. The mounting system underwent notable modifications after early operational experiences. The original design allowed for bottle jettison, but safety concerns led to a redesign that prevented mid-flight detachment. The performance capabilities of the JATO system are highlighted through its key specifications. Each bottle generates a thrust of 1,000 pounds, contributing to a total system thrust of 8,000 pounds. A standard launch requires the use of 8 bottles to achieve this level of performance. This additional thrust essentially enables the LC-130 to reduce its takeoff distance by nearly 60%. However, JATO production ceased in 1991, creating logistical challenges for ongoing operations. In response, the aircraft received new T56-815A3 5 engines combined with NP-2008 bladed propellers, ultimately matching JATO thrust levels while operating at lower temperatures. The evolution of JATO safety systems demonstrates a commitment to continuous improvement, informed by operational experience. In response to several incidents, engineers introduced essential safety enhancements. These included the incorporation of non-jettisonable bottle mounts to eliminate the risk of mid-flight detachment, the development of a synchronized ignition system to ensure all leak bottles fire simultaneously, and the implementation of mandatory pre-launch verification of the nose ski position. The system operates under strict protocols, as evidently demonstrated by the fact that once ignited, JATO bottles cannot be shut off until fuel depletion. The current supply of JATO bottles faces depletion, prompting the development of alternative thrust enhancement methods. Notably, the upgraded engine configuration now provides equivalent thrust capabilities while offering improved environmental performance. Cold weather modifications. Operating in polar environments demands extensive modifications to the LC-130's core systems at temperatures plummeting to -77 degrees Fahrenheit. These aircraft face some of the most challenging conditions in aviation. The LC-130's engines are specifically modified to operate reliably in the extreme cold environments encountered during polar missions. A critical requirement for these engines is the implementation of preheating procedures whenever ambient temperatures drop below -37 degrees Celsius, equivalent to -35 degrees F, ensuring proper functionality and preventing damage caused by thermal stress. Engine operations are also governed by precise temperature specifications for the lubricants used. For example, -20 3699 all is rated for temperatures as low as -40 degrees Celsius, while -7808 oil can withstand even harsher conditions, with a limit of -54 degrees Celsius, equivalent to -65 degrees F. These specifications are essential to maintaining engine performance in the most unforgiving climates. Recent advancements have further enhanced the LC-130's capabilities in cold weather. Upgrades such as the NP2000, T56 and 58 turboprop 3.5 system have significantly improved the aircraft's performance in icy conditions. These enhancements include a 20% increase in fuel efficiency, allowing for extended missions and reduced operational costs, as well as improved thrust generation, which is vital for takeoff and maneuverability on snow and ice surfaces. These specialized modifications ensure the LC-130 remains a reliable and efficient platform for polar operations. The hydraulic systems of the LC-130 are specifically engineered to overcome the unique challenges posed by polar environments. In extreme cold, fluid viscosity increases significantly, which can hinder system performance and reliability. To address these issues, engineers have introduced a range of critical modifications. These include temperature-resistant seals, designed to maintain their flexibility even in sub-zero conditions, enhanced pressure regulation within accumulators to ensure consistent performance, and adjustments to return system components to optimize functionality during cold weather operations. A key aspect of the winterization process involves preventing system binding, a risk that becomes especially pronounced at temperatures below -40 deg or ESF. These adaptations ensure that the hydraulic systems remain efficient and responsive in the harshest operating conditions, supporting the aircraft's mission-critical capabilities. Ensuring proper cabin pressurization in extreme cold presents several challenges. The system must address the increased likelihood of cabin leaks caused by the thermal contraction of materials, diminished efficiency of pressure regulation equipment under low temperatures, and the complex dynamics of managing pressure changes during altitude variations. Generally, these challenges intensify as the aircraft ages, requiring more comprehensive maintenance protocols. The system undergoes regular testing to ensure it can maintain proper differential pressure, particularly critical at higher altitudes, where cabin pressure problems have historically caused physiological issues among crew members. The maintenance teams have developed specialized protocols for troubleshooting pressurization issues ultimately leading to improved system reliability. These procedures include systematic inspection of components and regular monitoring of pressure decay rates. Therefore, despite the harsh operating environment, these modifications enable the LC-130 to maintain safe and comfortable cabin conditions for both crew and cargo operations. Landing gear engineering. The LC-130's landing gear system represents a remarkable feat of engineering, combining rugged durability with sophisticated shock absorption capabilities. This complex system has proven exceptionally reliable in meeting its design requirements across diverse operating conditions. The utility system primarily operates the landing gear, including doors and steering mechanisms. Essentially, the landing gear utilizes an innovative dual-mode configuration that enables operations on both conventional runways and snow-covered surfaces. The nose ski measures 10 feet long by 6 feet wide, whereas the main skis extend to 20 feet in length by 6 feet in width. The dual-mode system is characterized by several notable features. The ski undersides are coated with Teflon to reduce surface friction, enhancing performance on snow and ice. Each ski weighs approximately 2,000 pounds, providing the necessary durability for rugged conditions. Additionally, the system includes a retractable mechanism, allowing the aircraft to transition seamlessly for conventional runway operations. The landing gear system of the aircraft represents a relatively small yet critical portion of its overall weight, comprising approximately 5% of the maximum takeoff weight. This system is intricately tied to the broader weight distribution design of the aircraft, which has been meticulously engineered to ensure optimal balance and structural integrity during operations. The aircraft itself is designed with a maximum takeoff weight of 155,000 pounds, providing ample capacity to accommodate a maximum payload of 45,000 pounds. This precise calibration of weight distribution allows the aircraft to perform efficiently under a wide range of operational demands. The wheels, a vital component of the landing gear, are crafted with exceptional durability and resilience. They are engineered to support a staggering load of up to 30 tons while maintaining reliable performance even at ground speeds reaching 300 kilometers per hour. This robust construction not only withstands the immense pressures of heavy loads but also ensures consistent functionality across diverse surface conditions and varying load configurations, contributing to the overall reliability and versatility of the aircraft. The LC-130 employs oleo-pneumatic type shock struts, simultaneously utilizing hydraulic fluid and compressed air to manage shock loads during takeoff, landing, and ground operations. The impact absorption system is composed of several integral components that work together to manage shock loads effectively. It includes an inner piston assembly that is directly connected to the wheel and brake assembly, ensuring precise coordination during operation. Surrounding this is an outer cylinder, which is equipped with the necessary mounting connections to secure the system in place. A compressed air chamber is incorporated to absorb and dissipate shock loads, providing a critical cushioning effect. Additionally, the system facilitates controlled movement of hydraulic fluid through an orifice plunger assembly, allowing for smooth and regulated energy dispersion during impact events. The soft strut design ultimately provides numerous operational advantages, including reduced stress on the airframe and decreased maintenance costs. Through extensive engineering analysis and development tests, engineers have optimized the combination of strut air volume, inflation pressure, and orifice size to achieve optimal energy absorption characteristics. The system's performance has been enhanced through redesigned shock strut characteristics, specifically targeting improved responses during operations on rough surfaces. This modification has proven particularly valuable for semi-prepared runway operations, where impact absorption becomes critically important. Avionics and navigation. Navigating polar regions presents unique challenges The demand specialized avionics systems, the LC-130's sophisticated navigation suite, enables operations in areas where conventional navigation methods prove inadequate, primarily operating within the Arctic Circle, near the North Pole, and throughout Antarctica. LC-130 crews face significant magnetic interference that complicates GPS navigation. Rather than relying solely on modern systems, navigators utilize celestial navigation techniques. This traditional approach remains essential, as crews must calculate positions and headings using charts and formulas. The navigation suite is comprised of several advanced systems, each designed to fulfill a specific function essential to the aircraft operation. Celestial navigation tools are utilized for precise position verification, ensuring accurate tracking during flight. Digital cockpit displays facilitate effective flight management by providing pilots with critical real-time information. A multifunction radar enhances situational awareness by detecting weather patterns and potential hazards. Additionally, the air data computer plays a vital role in monitoring environmental conditions, supplying key metrics that support safe and efficient flight operations. Weather monitoring is an essential aspect of LC-130 operations. Relying on a comprehensive network of data sources, the aircraft utilizes information collected from over 40 automated weather stations, 3 United States Antarctic program stations, as well as various field camps and ships. Notably, the weather forecasting system generates approximately 9,000 air, ground, and maritime forecasts annually. The system processes more than 50,000 observations each year, essentially creating a comprehensive weather monitoring network across polar regions. The communication infrastructure has been significantly enhanced to ensure reliability in the most extreme conditions. The LC-130 fleet operates within a vast network that encompasses 1.6 million square miles of controlled airspace and provides flight-following capabilities over an area of 4 million square miles. This robust system supports nearly 2,500 fixed-wing aircraft takeoff and landing events each year, ensuring seamless communication and operational efficiency. MAX Center, the Joint Air Traffic Control Operation, manages these extensive operations. The communication system incorporates specialized protocols for situations with limited to no visibility, namely when land and sky blend without a visible horizon. Under such conditions, aircrews employ a distinctive spotting technique where co-pilots and loadmasters utilize flags lining the runway to guide the pilot during approach. The avionics suite has been upgraded with digital cockpit displays and flight management systems. These modifications ultimately enhance the aircraft's capability to operate in challenging polar conditions. The system includes secure beam line of sight BLOS data links and commercial SATM for increased reliability. Training for these specialized systems occurs at locations such as Raven Camp, situated 108 miles southeast of Kangerlussuaq, Greenland. This facility provides essential experience for aircrews learning to operate in austere polar environments. The training encompasses both theoretical knowledge and practical application, preparing crews for the demanding conditions they will face during actual missions. Performance capabilities. Beneath the rugged exterior of the LC-130 lies a sophisticated array of performance capabilities that enable operations in the world's most challenging environments. The aircraft's unique combination of power and adaptability sets it apart from conventional transport platforms. The LC-130 aircraft showcases exceptional cargo carrying capabilities tailored to the demanding conditions of polar operations. With a maximum payload capacity of 45,000 pounds, it serves as a critical asset for logistical support in the Arctic and Antarctic regions. The versatile cargo hold is designed to accommodate up to 6 pallets of essential equipment and supplies or transport up to 60 passengers in its dedicated transport configuration. Additionally, The aircraft can manage varied combinations of personnel and cargo loads, ensuring flexibility to meet the unique demands of each mission. The LC-130's operational range is influenced by several factors, including payload configuration and environmental conditions, which played a crucial role in determining mission parameters. The aircraft currently consumes approximately 5,000 pounds of fuel per hour, a factor that defines its effective range capabilities. For instance, with a maximum payload, the aircraft can achieve a range of 356 nautical miles. On a standard mission from McMurdo Station, it operates efficiently within a range of 1,800 kilometers. When carrying a reduced payload of 35,000 pounds, its extended range increases significantly to 1,636 miles. Recent advancements in the LC-130's propulsion system have substantially improved its performance, particularly in terms of fuel efficiency. The upgraded engines deliver a 20% improvement in fuel economy, allowing the aircraft to extend its operational reach and maintain longer flight durations. These enhancements are particularly advantageous for missions in remote polar regions, where extended range and reliability are essential for successful operations. The combination of increased efficiency and cargo capacity solidifies the LC-130's role as a cornerstone of polar aviation and logistics. The LC-130's takeoff capabilities vary based on surface conditions and auxiliary power usage. In situations involving sticky snow or heavy cargo loads, the aircraft relies on its JATO system. Each JATO bottle effectively provides 1,000 pounds of additional thrust for approximately 12 seconds, enabling the aircraft to overcome surface friction. The aircraft operates within a performance envelope that includes a cruising speed of up to 17 knots and a service ceiling of 23,000 feet when carrying its maximum payload. The operational ceiling can vary depending on factors such as cargo weight and environmental conditions, ensuring adaptability to a range of mission requirements. The upgraded NPMIDAS-2000 propellers, alternatively, have enhanced takeoff performance without JATO assistance. This advancement has proven particularly valuable as JATO bottle supplies become increasingly limited. The improved engine configuration similarly creates equivalent thrust as JATO bottles while operating at lower temperatures. The LC-130's performance metrics reflect its evolution from a conventional transport aircraft to a specialized polar operations platform. The integration of modern propulsion systems, coupled with its robust design, enables sustained operations in extreme environments. These capabilities support critical missions across vast polar regions, from scientific research to logistical support, making the LC-130 an indispensable asset in polar aviation. Structural reinforcements. Structural reinforcement stands as a cornerstone of the LC-130's ability to operate in extreme polar environments. The aircraft's framework undergoes extensive modifications to withstand intense stresses and temperature variations, essentially creating a robust platform for challenging missions. The LC-130's fuselage incorporates multiple reinforcement techniques to maintain structural integrity. The upswept aft fuselage, although necessary for cargo operations, accounts for 11% of total vehicle drag at cruise. Engineers have introduced several essential reinforcement techniques to enhance the aircraft's performance and efficiency. These include the use of advanced filamentary composite materials, which contribute to significant weight reduction. Boron divided by epoxy reinforcements have been incorporated, achieving a 13% reduction in weight while maintaining strength. Additionally, microvane technology has been implemented to reduce aerodynamic drag without compromising the structural integrity of the aircraft. The center wing box, primarily, requires particular attention in the reinforcement process. Recent modifications have focused on strengthening this crucial component to ensure airframe durability. The reinforcement strategy includes composite materials, that offer superior strength-to-weight ratios, besides enhanced fatigue resistance. The load distribution system within the wing structure is a testament to advanced engineering principles, carefully designed to manage stress and ensure durability under demanding conditions. Comprehensive load factor analysis has identified several critical aspects that underpin its functionality. Normal acceleration, for example, is meticulously monitored at the aircraft's center of gravity. To maintain stability and performance, the system adheres strictly to its design limit, ensuring that no load factors are exceeded during operation. Additionally, fatigue analysis is conducted using a sophisticated computerized monitoring system, enabling precise assessment of structural integrity over time. Reinforcements within the center wing box contribute significantly to the system's overall efficiency and resilience. These enhancements lead to increased aircraft availability by reducing maintenance requirements and improving the structure's durability, even in extreme operating environments. Furthermore, the reinforcement optimizes the distribution of flight loads across the wing structure, minimizing localized stress points and prolonging the lifespan of the system. The wing load distribution system incorporates a range of fatigue-resistant components specifically designed to withstand the rigors of continuous operation. Central to its design is the moment stress ratio, a critical structural parameter used to assess and predict wing box fatigue endurance. This advanced approach ensures an even distribution of loads across the entire wing assembly, maximizing efficiency and safety during flight. By integrating these sophisticated elements, the system exemplifies cutting-edge aeronautical design, providing reliable performance and extended operational longevity. The extreme cold conditions in which the -130 operates, with temperatures reaching as low as -77 degrees F, pose significant challenges to maintaining structural integrity. Specialized materials are required to ensure the aircraft performs reliably in such an environment. Thermal shock can affect seals and fabrics, potentially compromising their performance. Sudden temperature changes lead to material contraction, which can impact the feed and function of various components. Additionally, metal alloys experience stress variations under these conditions, requiring precise engineering to mitigate the effects of cold-induced strain and maintain overall structural stability. The aircraft's materials must meet rigid specifications for extremely low temperatures. Nonetheless, sudden temperature changes pose more significant challenges than steady-state cold conditions. For instance, when an aircraft moves from a warm hangar into cold, windy conditions, exposed surfaces experience rapid temperature changes. The structural design of the aircraft takes into account the various impacts of cold weather. It considers the temperature differentials that can occur within the thickness of materials, as well as the uneven expansion and contraction rates that affect different parts of the structure. Still, the cold preservation effect actually helps maintain certain aspects of structural integrity, although low temperatures typically preserve aircraft components better than harm them. Operational requirements necessitate active use rather than static storage. To manage thermal stress effectively, engineers have implemented a series of protocols aimed at maintaining the aircraft's structural integrity. These include regular inspections of structural components to detect any signs of wear or damage, continuous monitoring of the integrity of seals to ensure they remain functional in extreme conditions, and the assessment of material fatigue indicators to identify potential weaknesses before they compromise the aircraft's performance. The fatigue analysis methodology underwent significant changes after 2004, shifting from an economic model to a more comprehensive structural assessment. This modification primarily focused on evaluating multiple fatigue crack initiation points that could affect wing structure strength. Undoubtedly, this new approach has enhanced the aircraft's structural reliability in extreme conditions. The structural reinforcement system also considers the unique requirements of JATO operations. The additional thrust and associated stresses require specialized strengthening methods, otherwise compromising structural integrity during assisted takeoffs. These modifications ensure the airframe can withstand the intense forces generated during JATO-assisted launches while maintaining optimal performance in extreme cold conditions. The LC-130 is a true engineering marvel, built for the harshest polar environments. Recent upgrades, such as the NP2000 propellers and T56-815A engines, continue to push the boundaries of aviation technology. Do you think the LC-130 is the ultimate polar aircraft? Let us know your thoughts in the comments. If you enjoyed this video, don't forget to like and subscribe for more insights into aviation technology. Thank you for watching.